So last time we argued that if you take Maxwell equations and then you freeze everything at a given time so that you don't have any change in your fields with time, then the set of Maxwell equations, they split in two sets, right? One that is only it has to do only with the electric field, this, and then the other set that has to do only with the magnetic field. So that's a very nice feature of these equations, because you see in these static situations you can discuss independently the electric field and the magnetic field. I think that you are not able to do when you have all them mixed up. Also, vice versa, I mean, you can argue that it's true that the electric and the magnetic fields are connected, but only when they are vary in time. So if you have an electric field vary in time, you may expect some magnetic fields. In fact, then you have to solve the couple equations. And vice versa, if you have a varying B field in the game, then you will induce some electric field, and we will see that later on. But for the moment, we follow roughly the historical development in which they first discovered sort of these equations. I mean, as you see, this is essentially Coulomb law, as we will rederive in a second, and this we will talk about a little later. And what we said is that because of the properties of vector calculus, anytime you have a vector that is curl free, right, like the electric field here, that means that you can always derive this from a gradient of a scalar function. Okay, so this is a vector field. This is a scalar field, and every time you have a divergence-less field, right, this can always be derived from a curl of a vector that we call it A. And this, we call it, this is the scalar potential. They are lost in the storm. Okay. So here you have a nice exercise that you can try over the weekend. I mean, it's trivial. So to verify, indeed, that if you have a vector field, it's true that if you take the curl of the curl of a scalar field, okay, so this vanishes. So just plug in the components and verify that this is true. And also that if you have the divergence of a curl, of the curl of a vector, these two vanishes, okay? So that you, so that's an exercise. And we solve it together on Monday. So as I said, now we forget for a moment about the magnetic field, and we focus on the electric field. And this subject is called electrostatics, for obvious reasons. So the first things that we would like to see is that since what we knew about electrostatics is essentially the Coulomb force, that two charges, right, two charges attract and repel each other. In this case, they attract with a force that is proportionate to the product of the charges and inversely proportionate to the square of the distance. So how is this information encoded in these? I mean, they look very much different. how is this information encoded here, right? Because this equation it becomes sort of a constraint that allows us to write the electric field in terms of the potentials, and we are going to exploit this in a second. So the dynamical equations is really this, right? And this doesn't look much like F equal Q square over R square, so how do we get back that? I think this I gave it as an exercise, so but let's do it together. In fact, we can do both way, right? How do we get from this to Coulomb law and vice versa? By if you know Coulomb laws, how Maxwell, well, actually, not even Maxwell, but rewrote that force law in terms of this divergence of the electric field. So let's do the first things. So I know the Coulomb law because I've been in a laboratory. Hello, you made it. So we know and we want to compute to verify that indeed if Coulomb's law is true, then you have that the divergence of your electric field is equal to, is proportional to the density of charge. So to do that, we just hello. Okay, here they come. So to do that, it's easier to use this Gauss law in the integral form. So in the integral form, what you have is that the electric field, right? You remember if you have some surface, right? And you have this, okay, and then you have your electric field. Remember the electric field, okay. So the Gauss law tells you what happens if you integrate over this surface, and you start with a small area, like let's call it, I don't know, ds. The Gauss law tells you that if you take the component of the vector field, right, normal to this surface, and then you integrate, you get something. But here I don't know yet what that something is because I'm playing around and assuming that I don't know Gauss law. So if I have the electric field, I just compute this, I mean, not knowing anything, but I know that if I have some charges here, the force, okay, hello, is going to be Coulomb's law. So let me put the Coulomb. So I have a charge inside, for instance. And so the electric field is what? Is the, okay, so we're one by one they arrive. Someone still missing? Or? Okay. So we are rederiving Gauss law. From the Coulomb force that I assume you already know from previous studies. So to do that, I look at the integral form of Gauss laws, right? That is an integral over a certain surface, and I take this surface to include in the volume included by this surface, I have a charge Q. So I know that the electric field on the surface on this surface is what is, remember that the electric field essentially is, if you have test charge, right? Like this. Really, you should take the limit where this goes to 0. I mean, okay. All that stuff, but roughly is a unit of force, per unit charge, so that this is just like this is the other charge, and it's like the test charge, right? You go there with the test charge, and you measure what is your electric field there due to the other charge. Okay, so I should give a different name here. So this is like this. What? This one, you mean? Yeah. Well, just to keep track of the direction.
Yeah. No, just 1 over epsilon.
Ah, the 1 over epsilon.
1 over 4.
That's right. I did it in the Gauss units. Okay. I told you that this is going to be. So I will end up with a 4 pi instead of 1. So in our units, essentially 4 pi, I guess, is equal to epsilon naught, right? And ideally, that should be equal to 1, so that we don't have to worry. But unfortunately, here we are not. 1 over epsilon, right? So like this. But if they are equal to 1, then we are. You see, this is a problem with the measuring things, that you get all these units, and of course you would like some natural units, as you heard from. Arcani Ahmed, the lectures, it's very useful to use, right? Some units in particle physics, that is very easy, right? Because you put the H slash and C equal to 1, and you get this nice set of units. Here it's more complicated, so okay, this is just a joke, so don't write it. Okay, so we'll end up with the 4 pi instead of 1 over epsilon. Or I should put here, I guess. Okay, let's do it this way, so that we get the SI units. And okay, so I have everything because I used Coulomb law. So this comes from Coulomb. And now, if I do this integral, right, and I look what I get, I should get this, okay? Because then I know that. By using, I can transform this surface integral, right, into a divergence and get the differential form of the law. So how do I do that exactly? Well, I only have to do this. So how does it work? Maybe let's do it carefully. So I have, let's say this is this small surface. Now I take the other cut. So this surface has a normal vector that I call n, and here is the charge q. Okay, so the force you see is in the same direction as the r. So well, this is not. So let's put it here, so that I get. So this is the direction of right? And so if I take so this is normal to the surface, this is the orthogonal plane to R, okay, so here I identify an angle theta that I'm supposed to integrate over. So you see that the cosine of theta times the surface is equal to R squared, the solid angle over which I'm supposed to integrate. That means that here I can keep on going. Right, I have this 4 pi. So you see, this I get this is 1 over 4 pi epsilon naught. Okay, then I have this q over r squared. Then this term here, you see through these relations is just, so this is the cosine of theta ds, so I get r squared d omega. Therefore, I get exactly q over 4 pi epsilon naught. omega. And now when I do the integral over the entire surface, I only have to do the integral over the solid, the spherical surface that, the angle of a closed surface that you know is just, so if you do this, you get the 4 pi, right? 4 pi is if you go around, and so you see that you get indeed Q over epsilon naught. That of course this is, Q is what you get when you integrate the density of charge inside the volume is the total charge that you have. And in our case, I just had the Q. So indeed, I get that. So this is the divergence of E equal to Q over epsilon, right? But to get the divergence, I have to write Q as the integral over this volume. So I get the density of charge indeed. So, okay, this was kind of trivial, but it serves the purpose of really hammering in the fact that this is just Coulomb's law. It's just a cool way of writing Coulomb's law, okay? Instead of as a force, you write it as a property of the field, and then you connect the divergence of this field to the charges inside the volume. Of course, it's similarly simple to go the other way around. Because you see that if this is true, you just reverse your steps, and you rediscover that then the electric field is just what we wrote before, that comes from Coulomb's force. So you can go both ways, and this is really equivalent to this nice Coulomb force, the Coulomb's law, that maybe we write it here, that tells you that the force is 1 over 4 pi epsilon naught in this unit. If you have two charges, right, is the distance between these two charges square in the direction of this radius. So now we know that, and we have included everything that was known about forces between charges, static charges, into this law. Just to repeat it, this is equivalent to say what is in here, and what is in here is that you have a central force, remember, because it's like the Kepler's problem in mechanics. This is a central force because it points in the direction of the other charge. So if you have a charge, you have a force that is pointing there. So it's a central force that goes like 1 over r squared. This is the crucial information. And this information is translated into this equation, okay, these two. And also remember that you have this superposition principle that we talk about, because if you keep adding charges, then the force, the total force is just the sum of the individual forces of all these charges. Okay, this seems trivial, but it's not. As I said, there are forces in the world that do not obey this superposition principle, but here they do. So if you have to write, this was for two charges, but I can add a third charge. Okay, I can have, so the Coulomb force on this charge from this one simply add to the Coulomb force coming from the third charge and the fourth and the fifth and so on and so forth. This is encoded here. You see, it's just the density of charge, so you can integrate over everything. You just sum up to this total charges. So these three informations are in this very simple Gauss law on the divergence of the electric field. Questions? If not, so this was the, so let's stick now to the other equation and see what we get out of this, okay? So let me, that's a nice thing that, you know, the two fundamental forces in nature, they have the same force form, that is gravity and electrostatics. but the reason is that it seems that nature likes to work with this kind of two-body forces in which the total force is just the sum of all the other forces. And this happened for gravity, at least Newtonian gravity and electrostatics. Okay? You were about to... Yeah, I mean, as I said, this is a density of charge. So, you know, you have charges all spread around, and you simply integrate and you get the total. So you take chunks, you can take 3 chunks of charges, then you integrate, you get 3 charges, and they sum up in this. In a way, this is where the fact that you sum the charges to get the field is encoded in the fact that you can write the field in a way, because you only know what happens here. You don't care about the other, right? So. Yeah.
What does it imply, the minus sign there? The electric...
Well, this is the usual thing because the force, you remember like in classical mechanics, you want the force to have the, you know, to be attractive in that case, so you put a minus sign here. We already discussed this in mechanics.
Yeah, but here, I mean, the force is not always attractive, right?
Right, so you are going to get that I mean, with this convention, you get the force from opposite charges is attractive, and similar alike charges is. No, it's not conventional in the sense that we know that charges with the opposite.
I mean, because the cutoff field is 0 means...
Yeah, I mean, this is 0 independently of this, right? Then this is part of what you call the potential. But this goes in the same direction when we wrote, this was the same as the force, the link between the force and the potential in classical mechanics, that we wanted that by increasing the potential, you were getting a larger force. Here it works the same. On top, here you have these things with the charges, with the sign that you have to. Okay, but I mean, the crucial point is that you have a gradient here. Clearly, the minus is there because I put it there. So, what can we say about this? Maybe this is well, first two simple things. What are the properties of a scalar potential? Why is it called a potential, first of all? You know that this has to do with the fact that indeed this is a potential. That is something that only depends on the relative distances between the parts of your system, right? And this has to do that, you know, this is equivalent, right? The fact that your vector field, the curl of your vector field vanishes through the Stokes theorem is equivalent to the fact that if you take a line integral around the loop, right, of your field, this quantity vanishes. So this means that if you start here and you go around, and you come back here, right, and you do this integral, this gives you 0. So this is the L vector. This is E. I go around, summing up these components, and I get 0. But you see, this is really equivalent to what we know about a potential, because if you have a potential, right, remember gravity means that the potential here, the point A, and the potential in the point B, right, and if you go from point A to point B, if you wish the work done does not depend whether you go this way or you go this way, right? This was the property of the potential. You don't, if I tell you that the potential here is phi A and here is phi B, then the work is just the difference of, no? And I don't have to tell you how I go from A to B. This is the real physical property of a potential. A potential is useful exactly for this. But you see that if this is true, this is exactly the fact that it doesn't matter which way you go, because since if you integrate all around the loop, it gives 0, that means that you can go this way or you can go this way, and you get the same. So when I write that the force is this charge times the electric field, right? And the work done, therefore, the work done in this field, if I take this charge and I move it in this field, the work done is, okay, you get the minus. So from point A and point B is what? The force, right? Work is always this line integral of the force along the L, okay? But I can replace the force with the because of this definition, I can simply replace, I put the Q, I guess I put a Q here, and then what I'm really doing is the integral of the E field along the L. And you see then this property comes here, is exactly what I told you, right? Because now I have to do this integral from A to B. This is the work done in moving my charge Q from A to B. And so you may wonder, this depends on which way I go from A to B. But no, because you have that E is a curve-free field, it does not depend. Therefore, this can really be written as a potential. In fact, you verify that because of this, I can write my E field as the gradient, as a gradient of a potential. So I have this minus here. So I get the integral from A to B of the gradient of this potential, of the gradient of this potential along this line. And then you see that exactly because of this, you get the simply is the integral from A to B of d phi, right? Or Q times the potential in A, in B, minus the potential in A. So indeed, that is a potential. And the difference between the values of the potential in two different points of your field times the charge is the work to bring that charge from one point to the other one. It does not depend on the. So in the case of the Coulomb, you know that the force lines, right, are, because the force is central, so it points along the direction of R. So if I have a charge Q here, my force lines are something like this, right? And therefore, the equipotential spheres or line on the blackboard are going to be just circles like this around this charge. Okay. So along these circles, really they are spheres. This is phi equals a certain value. It's constant along this line, and you do work only by moving from here to here. You do some work. But it does not depend the way you go from here to here. It just depends how far you are from one point to the other, away from the. That's for the Coulomb field. That is the simplest one, for which you have those very simple. You see, it's nice to. This is the Faraday's way of doing computations in electrostatics, just by drawing the force lines. Okay, so there are lines along. Along which the field is tangential. So in this case, the field is just radially with respect to the charge, and so they are straight lines. And then the equipotentials line, they are orthogonal to these force lines, right? Because they are the gradient there. I made a mistake. Where work is minus no, you see that. Well, I mean, Well, so no, the conservative, it means that it does not depend on the path.
So energy is conserved.
Yeah. So
It's minus change in potential or positive change in kinetic energy.
no, I mean it has to do with this too. I think this is the correct.
Because work is positive change in potential in kinetic
Yeah,
energy.
but I mean, I move from a point A to a point B, right? So, well, you say? Say again your point. So the
The force is our electric field is conservative.
yes.
The energy is conserved. So work is positive change in kinetic energy. So that translates into minus change
No,
in
but
potential.
there is no kinetic energy here.
Yeah, if I start from conservation of energy,
Yes.
work is change in kinetic energy. So it is minus change in potential.
No, I mean
Here it is positive change in potential.
But why? I mean, this is a positive change in the potential.
From work
If you pull it up, right? You start from here, you move it up. It's like in the gravitational field. So with this definition, from here to here, I'm doing some work. If instead from here to there, the system is producing work because you lose potential energy and you gain kinetic energy if you want. But here I just put in positive energy in the system by doing some work with this definition. So I think it's always conventional. I mean, remember the potential. I mean, it's like in mechanics. It doesn't have an absolute meaning. Okay, the only thing is the force, but the connection you put here is okay. So much about Coulomb's law. Maybe I should say just very quickly, you may wonder about all the stuff that you learn about electric circuits, right? Because you say, where is Ohm's law, for instance? Here. Okay, it's here, obviously. But we won't be doing much about that. I mean, of course, it's a huge subject by itself. But I assume you already know a lot about all these things, about circuits. If we have time, we will talk a little bit about more interesting circuits that are these oscillating circuits. But for that, we need some extra information, so we will come back to that. But here, the Ohm's law, the things that tells you how the drop in electric potential that we are talking about along, say, a wire is related to the current. In this context, you should think of the Ohm law not as a density, right? So you see the density of current is proportional, let's call it sigma, to the electric field. Okay, so that's the differential form, or the microscopic form. So these are densities, and Ohm's law, it's an approximation, right? Like those relations that we wrote the other time between D and E, right? Because it's, in a way, it's a form of D, because it's a very peculiar form, because you put the electric field in a very strange and peculiar kind of matter that is a conductor, okay? Like a wire, and that is a metal, and in the metals you have the electrons on a common band, and so they are sort of very much free to move about, and so you have an electric current that if the first electron moves a little bit, the last one moves more, and you have this, okay? And so this approximation tells you that if you have an electric field is directly proportional with some constant here that maybe is not really a constant if you have a wire with some structures, because it may depend on the point, right? So this may be a function of the position, and may even be a tensor, unfortunately, if it's not uniform, right? So, but let's assume it's a thin wire, so this is really just a constant and is uniform, because that's what Ohm's law is talking about, a uniform, thin wire, conducting wire, and then you have that the density of current is directly proportional to the field that you apply. And so this is called electric conductivity, obviously. And so say 1 over this is going to be proportional to what we call the resistance. That is the opposite. You know? This is how easy it is to produce a current by applying an electric field. The resistance is just the opposite. So I don't want just to make contact with what you knew about this stuff. In this language, so the V, the electric potential, right, is exactly like I wrote it before. So you have a wire at 2A and B, right? So this is going to be just, well, let's call it 1 and 2, that is easier. It's just the difference between the potential that I wrote there between these 2 points, right? So you just do an integral between 1 and d phi. So this is the drop in electric potential between 2 points on your wire. And you can also put, I guess I should put a minus. And by the usual thing, this d phi, what is it? Is the gradient, right, of phi times the ds, the surface, the little ds, I mean the little ds, not the surface, the little dl along this wire. But this is minus the gradient of phi is what we call the electric field, right? So this is just, and then by Ohm's law, I can rewrite the electric field there as this integral between J ds divided by what I call this conductivity, the electric conductivity. Now, if I assume that everything is uniform, so this is a wire that is uniform and everything is nice, so then J, right, times this little area is just what I call the electric current, that is the current that goes. So I can pull it out, and I'm left with an integral over this ds divided by sigma A, where A is this cross section. And I guess this is what you call this is what you call R, the resistance of the wire. So okay, nothing really deep here, but just to say that we are still doing what you learn about electric circuits. It's just we are doing it using these differential forms that it's more appropriate when discussing fields. But at the end of the day, you recover Ohm's law, that I guess is this one, V equal to and later on we will see that we can recover also the other that has to do with the inductance and the capacitance of a circuit, that are the other two properties. So now I don't know whether to leave some stuff to the exercises. Because what is left I mean, there are two things that we need to know. How do you use this law to derive the E field for different charge distributions, right? Because after all, we want to solve these equations and find the field. So this is the one point of view that is given a certain charge distribution, that is this. What is E, right? I guess this is what you want to know. That means solving this equation means exactly this. So, of course, this is really part of the homeworks. I mean, I give you some charge distribution, and you, by solving that or by doing some other, or by using Coulomb's law or whatever, you come up with the electric field the corresponding electric field, okay? So here we have a long series of homeworks. Have you, how much homeworks already? Just 3, so we can. So then on Monday we solve. So some I'll do it here together today, and then the others we do it on Monday together. Just to give you, as I said, I mean, I give you a charge, for example, this I leave it as a homework. It's the next level of difficulties. So Coulomb law, it's clear. You have a charge, you get the field through the Coulomb law. What happened? So this is the homework. So this is number 4, I guess. Just 3. I think I remember more than 3. No, what are these 3 problems? Tell me. No, the one that you are supposed to solve Monday. Yeah. Right. Yeah. Okay. Okay, so I mean those are really quick. So Coulomb law has to do with one single charge, right? You have a single charge, you get the field that we know. So what happened the next? You will see this is something that will come up very often because in a way it's very important. Is the next term in expansion. What happens if you have this other situation? You have 2 charges, 2 equal charges. Let's call it E. That is nice, like the electron. So plus and minus, okay? To a certain distance that I guess here I call it A. So not 1 charge, but 2 charges at a certain distance A. So what is the electric field of these 2 charges? If they are, you are far away, say, so you can do so you are here, distance R. So you want to write the field for this charge distribution. I know it's just a superposition of, as I said 5 minutes ago, of 2 Coulomb forces, but do it in a more interesting, because very often this happens that these 2 charges are very close to each other and you are measuring the field very far away, okay? So assume that this R is much larger than A. You understand that you can do some expansions in this 1 over R square and derive the potential, so the potential phi, okay? I mean, I already know that this 1 over 4 pi epsilon 0 ER, say 1 minus ER2, where this is R1, R2, okay? But do the expansion in detail, so do the expansion, and then you introduce this vector P that is just the distance A. Okay, so if you introduce some axis, right, so that this is plus and this is minus. So this P is the distance A times so it's a vector that points from minus to plus, so this way, and the value, the absolute value, is just E, so the charge. This is called the dipole moment of this distribution of charges. It's a very important quantity. So this is an important exercise. You will see it will come up over and over again, because essentially, as we will discover, I guess, on Friday, when you have an arbitrary distribution of charges, you can do some expansions, and then you have a leading term that is the monopole, that is like having that charge, that distribution of charge all concentrate in some point. Then you have the dipole, that is the first correction, that comes from something like this, and then you keep on going, you have the quadrupoles, and so on and so forth. By the way, this is completely equivalent in gravity, because it's the same kind of force, right? And there too, if, as I said, right, already I told you, if you look at the sun, you have a first term that is the monopole. Then there you don't have the dipole terms, as I told you, because you don't have, I mean, E, there is no minus E, because the mass is always attractive, so this term is 0. So the first correction is a quadrupole. So the first correction to the orbit of the Earth, due to the fact that the sun is not a perfect sphere, is a quadrupole correction, not a dipole. But for the electric field, this dipole is there, and of course it's very important. You will see it comes up everywhere. When you listen to the radio on your car or at home, that radiation is essentially due to dipole radiations. That is, you have two charges moving, and that is an antenna. It's called a Marconi antenna, and that is the simplest way to produce an electromagnetic wave. And then on this frequency, you modulate that, and you listen to all the nonsense that comes through the radio. Okay. So try this simple exercise. So the exercise is first compute the potential, assuming this thing I told you, that this distance A is much smaller, so I want some expansion in this, right? So write the potential. So you must be able to write this potential in terms of this dipole moment. Maybe I write it here so it's easier. Verify, so let's turn it around. Verify that the potential is this, where P is what I defined it there. And it points from minus E to plus E. So you see, it's a field that goes like 1 over R squared, and is proportional to this dipole moment. 2, compute the electric field. Okay. So you must. So here you start cranking in this calculus, vector calculus. So you have to take the components and take gradients of the component, and you derive the electric field. That maybe I write that too, so that you check. So if I call, so I write it this form, E3. So this is a unit vector in the direction of R. Minus P. So this is the electric field that goes like a cube right here. So this is a unit vector in the direction. So this is the projection of this vector in this direction. Okay? So just check that this is, and draw the force lines of this field. Okay? So I don't know, you have this is P, then you draw your, here you will get all the components, so you will be able to draw the force lines. They look something like this. Okay? Um, is this clear? Can I? So this is it's an example, a very important example of how you get the field by means of using Coulomb's law directly. Okay, so that's the easiest thing. I didn't. We could have done that the first day without introducing all this Maxwell stuff. But then you can also say, well, I want to use Gauss' law, and so I want to compute the electric field directly from Gauss' law. And you understand that unless the geometry of your charge distribution is particularly simple, this is going to be complicated, right? Because if this guy is very strange, then you need to do some strange integral to get E, right? To solve this, these differential equations, and then you need a computer, essentially. But if the geometry is very simple, then you are very much in luck, because then it's, you think of this equation in the integral form, and then if the geometry is simple enough, then you may be able to do the integral just by, if it's uniform distribution with the simple geometry, the integral, as I did in proving the relationship between this and Coulomb law, you don't really have to do the integral because everything is uniform, so you sum up. So maybe if I give you an example, this is, it's even, the simple example, so this is an example, is if you have a distribution of charge that is simply an infinitely long line, right? You have an infinitely long line charged. What is the field? What is the field around this charge distribution? So we discover what the field is for a point charge, and is the Coulomb field. The next, it's like a Euclidean geometry. After the point, you have the line. So, okay, here's the line. So instead of having just a point charge, you have a line infinitely small, but infinitely long, that is charge. And how do you define the charge there? Well, so let's assume that it has a uniform charge density per unit of length, and I call it lambda, because it's the Greek equivalent of L. And you see that now it's rather simple, because all I have to do is to think of that Gauss law in terms of integrals that tells me that the surface integral of the normal component of E, right, around the surface is equal to the volume of the volume integral of the density of charge included in the surface. So here I just have to be clever and so I take as my surface just a cylinder like this going along this line. So this is my surface integral, okay? Therefore, the electric field, right, the normal component of this field is like this. And therefore, I have that locally here, right? I have that E, the normal component, is just 2 pi. So if I call this distance r, is 2 pi r, right? This is the... Then I should integrate along the entire line, but I take just the unit of length. So per unit length, this is the surface integral. And that tells me that how much charge is inside this little volume. The unit volume is lambda, right, by definition. So here I put lambda, and I have this famous epsilon 0. So you see, in this case, I get immediately that my electric field, first of all, is pointing normally to this wire, this because of the symmetry, right? I mean, and then the value of this field is just lambda divided by 2 pi epsilon naught 1 over r. So here the field does not drop like 1 over r squared, like for the single charge, it goes down like 1 over r. So it's lower because you have this infinitely long charge, so the field is stronger.
I want to know here, lambda, if the charge is lytic,
No, the charge is
dynamic,
is uniformly distributed along this wire.
okay, so now if I want to take the integral.
No, this is the integral. No, this is the integral. This is the integral. This is the integral will also this infinitely long, but I just compute by unit length. So let's call this 1, L equal 1. So I do this integral. This is what it is. So if you want here, you have a delta L, but of course if you integrate, you get, but you have an infinite value here and there, so you sort of drop it. So that's why it's called by unit length. So you see, if the geometry is forgiving, then you can do that right very simply. The next level, I guess, so point, line, the next level is a plane following a classical geometry. And so you may wonder, so this was the field for a line charge. So what is the field for a uniform sheet of charge? Right, so it's a plane, an infinitely large plane covered with a certain charge, right? So it's like something like this. Infinitely long charge. So how big is the field? So this is a uniformly charged plane. Again, I do the same trick, right? I use a small, for my volume here it's a bit, no, like this. It's a little bit, so you take, as again, you take a unit volume and you integrate. So this is your Gaussian surface over which you do your integral. And again, this integral is equal to the total charge inside the volume, inside the surface. And so let's call, now again, this is a uniformly charged sheet of something. It has, let's call sigma again. This is the unit, the density of surface charge per unit area. Okay, it's like before it was the density of charge per unit of length. So again, because of the symmetry, the electric field should be on both sides, something perpendicular to the plane, right? Because there is no way that it cannot be perpendicular. So you take this very small. It has no component on the side, so there is no leakage. So if you call this unit of area A, you simply have that on this side you have E times this area when you take the integral of the normal component of E. So I keep on pointing here, but I keep on thinking of the integral form. So I hope at this point it is clear for you. I mean, they must be completely equivalent in your mind. So I point here and I say, so you may wonder what is he saying? I mean, there is no integral there, but there is an integral if you use the integral form of that. So I have from this side and also on the other side, so I have, this is the total flux of E outside this little tiny box. And this must be equal to 1 over epsilon naught, right? This one, the integral over the volume included in this little box of the charge inside. So this is just sigma, right? And sigma times the area. So again, the unit area, you see, can drop out, and you get that the electric field, arbitrary point here, right? Because this I can move it up is just sigma divided by 2 epsilon 0. So the field gets bigger and bigger because now it's constant. So you can be very far away from this infinite sheet of charge, and the field is the same as if you were very close. So there is no way to know how far you are from these things. Okay? Actually, again, if you are thinking of Ohm's law and all that kind of stuff, this sheet of charge should suggest to you the idea of the capacitor, right? The capacitance of a system. So maybe, well, the next things. I mean, what happens if you take two of these planes, these two charge sheets, you put one next to the other, right, like this, and also you take opposite charges. The density of charges of one has the opposite sign. This is a very well-known component of many electric circuits, even though there is not, I mean, in the computer is not realized with this metallic planes, but the idea is the same. So what is the electric field between these two sheets? Yeah. Okay, so I'll leave it as a, since you already know. So this is homework number 6, I guess, now. So what is the field inside? So it's the generalization. Here's just one sheet, and there you have two of these uniformly charged sheets of charges with the opposite charge, okay? So call it still sigma, and what is the electric field inside? Also, what is the electric field outside?
0.
Okay.
Minus sigma over 2 epsilon 0.
0, okay. Then, okay, so that you already know. So, but then please compute the potential. So the potential due to that field inside, and prove that you have that this potential, let's say call it V, well, that you know is equal to the, let's call it, okay, can be written in this form, right? So this is the charge that you put here, and this new quantity that is the capacitance is equal for this case is equal to epsilon naught, the area, the unit area, divided by the distance between these two plates. Again, a result that you may already probably know. This is just, okay, it's a simple exercise just to connect with what you know about these things, that is, these macroscopic quantities like the capacitance. And if you feel really inspired, you could do the same for two spherical shells, right? Meaning, instead of a plane, I take a shell, and then another shell, metallic shell, inside the first one. So I call R, I guess I call it R1 and R2, the radii of these two shells. And you put a charge Q on the inner one and a charge minus Q on the outside. And you do the same trick. You compute the potential, right? You divide the potential by the charge, and you get the capacitance. And so the capacitance is this charge Q. So maybe here should be Q. Divide by the potential. So you compute the field, you compute the potential, then you take Q over the potential, and you get this quantity, why this quantity is singled out, why we single out the capacitance in the system, because you see it's a purely geometric quantity. It has nothing to do with the charge. It's a geometrical quantity that is completely defined when you give the geometry of your system. So for the two infinitely large, uniformly charged planes, it's just this. And I want you to do the exercise and show that for this charge distribution, two spherical shells, one inside the other, it's just given by some ratio of this radii. In fact, it's the product of R1 times R2 divided by the sum, the difference. I mean, this is also known as 1 over R1 minus 1 over R2, obviously. I mean, 1 over this. Okay. So, I mean, of course, we can keep on going. But so let's just stop here with the, I mean, for the exercise. Of course, a byproduct of that exercise is that by means of the Gauss law, it's very easy to compute what is the potential inside a charged shell. Okay, so that you can do too. But it's pretty obvious that it is zero because of the property of that, right? So if you have charges on a metallic shell, they distribute themselves in such a way to make zero the potential inside. Okay, that's also true for gravity. I mean, if you have a gravitational shell, the gravitational field inside the shell is zero. Okay, this it only comes from Gauss law. It only comes from the 1 over r square dependence of the force. So a way to screen yourself from the electric field is to go inside a metallic shell. What is the electrostatic potential energy? Okay, so let me just, I want to write, because it will come in important later on, I want to write the potential energy. So the potential energy, right, now I call it W, for a certain charge, so I for a charge Qi, due to the potential at that point, okay, it's easy because we know that the potential there, due to all other charges around, right, because of this superposition principle, is just 4 pi naught, then the sum of all these charges. That's what I said. So let me sum from 1 to n minus 1 so that I have the one left. So Qj, and then the distance between, right? This is Coulomb law one more time. And now I want to massage these things in such a way to get the total energy, right? Then it's going to be just the sum of this. The total energy is just 1 over 4 pi epsilon naught. Then you sum over all possible charges Qi, so from 1 to n, and then you sum, you put that is the j from, say, in this case, j less than I, right? Because they go one, two bodies. So the total energy in this system, because of the interaction of the I charge with all the other n minus 1 charges, is this sum, double sum, of the product of these. Very good. But now, so that is what we already know. Now I want to switch to this density of charges because I want somehow to bring in the electric field. So I can replace all these charges and these sums with some integrals, right? And I have because at this point, if I integrate over the all volumes, I get a factor of 2, too much. So I divide by that, so I get 8 pi naught. Then I replace these sums, right, by 2 integrals over the volumes d3v prime of some density of charges at the point r in this volume and a point r prime in this other volume. And downstairs I just have this 1 over r dependence that is characteristic of the electric potential. Okay? But you see that this part here of the integral, so this integral here, is just, I can rewrite, it's just the potential in the point r. So that quantity is 1/2. Well, let's do the intermediate step. Is 1 over 8 pi epsilon naught what? Yeah. So this, you see, this is just the potential due to this charge distribution in the point r. So that I can write, I mean, 1 over 4 pi epsilon is the potential. So I get 1/2. Then I can integrate the density in the point r, and instead of doing the other integral, that integral itself is just the potential in r due to the other charge distribution, right? So this is again the potential, the energy of a system of charges written in terms of the density of charge in r and the potential due to the other charges computed in r, and then you integrate over this volume. And now I can use the yes. Which one? This or this? This one. I take, you see, this is the potential in the point r. So if I rewrite this in terms of the charge density, this is exactly what I call the potential. So I can rewrite this part here of the integral, well, not this one, but as exactly, yeah, this one too, as exactly as the potential. Then I just have to do the remaining integral over the volume V. And why I'm doing this? Because now I use the, you see, if I use Gauss law and I apply this to the d phi, right? D phi, you see, with the minus, this is equal to rho epsilon naught. Okay, but this, the divergence of the gradient is what? Is this delta square, right? This is an equation that we are going to discuss. So if I use this, if I put this scalar potential into the Gauss law, I get this equation, remember that we derived the other time, and I call it the Poisson equation. This we are going to discuss you will see, in many details next time. But let's just take it from as a consequence of Maxwell equations, and I can put it inside here, right? Because you see this integral, this rho, I can use the Poisson equation and rewrite it as, I have a minus, so minus epsilon naught divided by 2. Then I have this phi, and then I have the Poisson integral, the Poisson equation in this form. So through I replace rho, the density of charge, by means of the Poisson equation, that is just Maxwell equation. So I go from here to here. And then I do this integral by parts, to get, so by part, I have one part that goes very far away, and as usually I drop it, and minus, so I get epsilon 0 divided by 2, so the minus become a plus. And then you see, by parts, I have this becomes just the gradient, and then I have a gradient acting on the first function. So in other words, I just have a gradient square, right? But what is the gradient of phi? This is just the electric field. So this is a very nice expression because I have that the square of the electric field integrated over the volume is just the energy of the system. Or if you want, you can define an energy density that is a little w, such that when you integrate over the volume, you get the total energy. Your energy density, if you have an electric field, is just this. So in a region of space where you have an electric field, you have a density of energy that is just like this. Essentially, this depends on the units, but is just proportionate to the square of the length of your electric field. Okay? Okay, I stop here because I have to catch this bus. But this will come useful because then we will see what is the contribution of the B field to the energy of the field, of the energy of the total field in a certain point, and that will be useful. But otherwise, this is... Okay, so next time we will start from here, from the Poisson equation, and essentially we will try to solve this equation. So, you have seen three ways to solve Maxwell equations. So briefly, either you use the Coulomb law, as you are supposed to do for the dipole moment, and then we discuss on Monday, or you use directly Gauss' law if the geometry is simple enough, again, as we have seen for the wire, and you try for the spherical shells. And the third way, as you see, is by moving from Gauss' law to the Poisson equations. They have the same physics, but this is sort of simpler, even though it doesn't look like. And then solve this systematically. And that's where most people in the 19th century try. I mean, they wanted to solve these equations in a systematic way, and you will see there are several techniques that then are used in many different fields in physics. As I said, orthogonal polynomials are used here to solve. There is a very nice feature that, if you remember, in two dimensions, analytic functions, you remember this? Analytic functions, Z, in two dimensions, they are analytic, they have these Riemann relations, right? That the cross partial derivatives in the X and Y direction, and they are equivalent to this. So all two-dimensional electrostatic problems can be solved by, if you find the analytic function satisfying the appropriate boundary conditions. So that's where most of this stuff on analytic function comes from, anyway. So we will spend some time there and then move on.